Welcome back, everyone. We'll start in just a few moments, however long a moment is. Well, it's time. Welcome back, everyone. It's now the spring 2026 semester. And sorry for that frantic message this morning. I noticed just last night that there was supposed to be a class in this room that ran to 12:50, which makes setup kind of frantic for me on my end. But there was no class here, so I don't know if they moved them or what's going on with the schedule. We'll see what happens on Thursday. So if I'm a little bit delayed getting things set up, then you're always welcome to say, well, hang out with me in the hall if you're here in person while we get ready to charge into the classroom at about 12:55. I think that's about fair. Or if you're coming in through the online section in Zoom, you're welcome to just join the Zoom meeting. You can be in that meeting without me there and just hang out until I log in. If I'm a little bit delayed, that's going to be the first thing I do is just log into Zoom. Turns out I have to log into a lot of things. This computer's been updated, so the Windows environment just totally resets every single time I log into it. So everything has to be customized, but we'll get through it. Well, any questions to start us out at the moment, folks? Okay, well, our goal today is do a quick reading through the syllabus, mainly just focusing on how the course is going to run those kinds of elements. We'll go through everything we have on the Canvas webpage and get started in section 2.2, Booleans, numbers, and arithmetic. First, because this is kind of a strange course, I think a good place to start is the Zoom environment and how it's going to run. Really, this is two sections glommed together, the in-person section, 05, the fully online section, 15. And if you intended to be fully online, but you're here in the 05 section, I don't really care. It doesn't really matter too much to me. The class sizes is full on either end from what I saw. So if you're in the wrong section, it doesn't make that big of a deal, really. But because of the challenge of running two different kind of class modes at once through Zoom, and they only provide one monitor here, I want to give everyone who's in the Zoom meeting before we start today just a good idea of what it looks like on my end. So let me change this out just a little bit. Expand this here. Okay, so this is what my Zoom environment looks like from the desktop. And it gives you a good idea of how the course is going to run and what adjustments we have to make. And I didn't mean to do that. Oh no, how do I fix it? Whoa, hang on, I kind of messed up my controls here. Okay, so here's the screenshot I wanted to show you. From my desktop, this is what it all looks like. Imagine the white behind here is our whiteboard where we're going to be annotating the course notes going through the lecture. I'll have the Zoom control up here, which sometimes auto hides. It's hidden right now, so I can only see that strip. And as far as this goes, I have to hide this right away because as you can see, that's more for like a separate monitor, maybe something clear over here or a top so I can actually see those. The first thing I actually do is just hide this whole thing so that my view updates to just who is talking right here. And I'll be trying to do my best to pay a lot of attention to this segment. So anything you do for along the lines of showing reactions and those kinds of things, I have it hidden right now. Let me pull it back up. I'll try my best to pay attention to those so I can see how you're doing a course. If you have a question, you could raise your hand. But if you have a question, you can also just immediately interject with your microphone. That's just fine as well. The other way to participate is through the chat right here. That doesn't really show up. Through the chat right here will work as well. That one's a little bit more tricky for me because it sends a little notification here that I have to notice. And the screen's pretty busy, so it's something that I might miss. So if you do send a chat and I miss it, but someone else in class notices a chat came through, don't hesitate to just say, hey, Mike, there's a chat in Zoom. If you're in person or in class, that's going to help me out a lot. We'll get better at this as we go. We get a little bit rusty over the winter break. But just to start us out, because it's a weird class doing it this way, some people have probably done it before, but if this is your first time doing a hybrid, in-person, fully online section all in one. This gives you an idea of how the class is going to run. Any questions at the moment? Okay, let me close this out. Well, let's open up that syllabus. Like I mentioned, you probably have already taken a quick look at it, so I'm not going to do a careful line by line reading. The first thing that we've been talking about so far in this class is that there's really two sections running concurrently, same time, but different places. Other most important thing I would mention is, as far as this class goes, there's really two ways to do office hours. You can do office hours by showing up in person to the classroom down here in Idaho Falls, CHE 215. It's going to be 2:30 p.m. to 3:30 p.m., basically right after class, Monday through Thursday. So that's a great way to participate. You can also just join the Zoom meeting. And like I mentioned before, not too worried if you're in the in-person section or the fully online section. Anyone can show up in person to the classroom. Anyone can show up on Zoom. So I'm not going to say, hey, what section are you in, to determine if you're in the right place at any time whatsoever. So this is the standard office hours. Another way to do office hours is exclusively through email if you'd like. I'm pretty responsive on my email. I try to reply to messages as soon as I see them. If you send me an email now, I'm ignoring it because I'm in a class meeting, of course. But you can send me just about anything through the email. General questions about the class, homework questions if you get stuck on a problem, anything along those lines. It can turn into a kind of office hours. It's just a little bit slower. So if you're, say, working homework on the weekend, if something just seems a little bit weird on the homework set, don't hesitate to email. I'll be happy to help out. Well, aside from the contact information, office hours, that kind of stuff, the next exciting thing is the textbook. You can buy this if you like, but it's available completely free. Here's the ISBN, and our textbook is this right here, which is kind of nice and exciting for this class. If you click on that link, it takes you to this. It's kind of an archaic looking website, but it doesn't have to be fancy. This is the entire textbook. Chapter 1, the point of this book is pretty interesting motivational reading. We're starting in Chapter 2, the basic data types. So click on that. It's 94 pages long since it has multiple sections. And this is essentially our textbook. I assigned section 2.1 as reading, but it's a really short blurb about what we're doing in this book. And the course really starts in earnest in section 2.2. And just like a traditional textbook, if you go to the very end of the section, here's where the homework exercises are. Our author has a lot to say. Before we get to the homework exercises, these are really kind of interesting and fun to read. Sometimes they get extremely technical, so some of them are tougher to read than others, depending on your background. But keep going to the right, and eventually, this is the homework exercises. So I'm assigning exercises sometimes straight out of the textbook, like you see here. Sometimes these exercises get very, very technical. And so occasionally I might have a PDF version of the exercises, just some custom ones that I've written out that goes a little bit better with the level of the course. So far that's pretty much how the course is going to run. We know where to meet. We know where the textbook is. The homework sets down below here are going to be posted as just basically a little link like this. Clicking on that reveals the exercises, the ways you can submit the homework. I have 3 different options, and I'm doing this for the very first time. All last semester, I just totally blocked out that option because I was worried about how complicated it might be. So I'm going to try to see how this runs for the very first time this semester in Canvas. So if you want to just upload your homework assignment directly into Canvas, that'll work fine. And again, that's for anyone in the class, online or in person. You'd have to upload a PDF as the most compatible file type. But you're also welcome to just say, download the homework file, work on it digitally, convert it to a PDF, and just directly email it to my ISU email address. This is pretty much how I accepted all homework assignments last semester, just direct that way. I feel like sometimes Gmail is a little bit more robust than a brand new system like Canvas that just got implemented. But if anything goes wrong when you're trying to submit your homework, that's always going to be just fine. That's your sole method you'd like to hand in homework, they'll be totally fine as well. And if you're in the in-person section, or if you happen to be on the online section, but you're in town and you just want to drop in class room 215, you can just hand in a hard copy right before or after class, and that'd be just fine. So you can work on these homework assignments in multiple ways. You can submit them in multiple ways. If you're working just ordinary paper, then you'll have to take some screenshots of that homework. If you're working digitally, you might have to convert it to a PDF. But essentially, that's so far the major nuts and bolts of how the course is going to run. That's 10 minutes of talking so far. Any questions at the moment?
So is there a specific file that we download with the questions on it, or do we just like work on those questions from the?
Yeah, for this assignment here, it'll just be working on these specific questions that you see here.
Okay, so we just work on them from the textbook.
Sorry, say again.
We just work on them like directly from the textbook.
Yeah, exactly.
Okay.
There'll be some occasions where I do write out a custom set of exercises. And what you'll see here instead is a link to a PDF. So I'll give a heads up to the class when that happens. So occasionally there'll be just a file to download, but for a lot of the times, they'll just be exercises directly from the book. Other questions so far? Okay, well, let's see where we're at in the syllabus so far. So we went through the textbook. I'll leave some of these things for your reading, like the prerequisite course objectives. As far as the homework goes, we kind of touched on it quite a bit. At the end of the semester, I'm going to drop the lowest 2 homework sets. And when it says homework will be assigned for each class meeting, well, that kind of just depends on the pace that we're going to go. Really, every homework set, say assignment 2.2, is going to be tied to a relevant section out of the book. So here's section 2.2. The moment we complete this section 100%, that means the assignment is considered to be fully assigned, and the due date is always going to be 1 week away from when we complete that particular section. So if we took, say, a little bit extra time in section 2.2, I'll just push out the due date so that it's always 1 full week ahead. And let's see here. Here, this is just information saying that for your homework sets, you do have to write out step-by-step solutions. But I think we expect that usually in a math class. That's how we're going to write out our solutions on a real exam setting. I'll emphasize correct mathematical notation, but always give you a heads up of, hey, be sure to write this on those kinds of things as the occasions occur. Answer is given in simplified form. That's just a generic statement, really. They must be given in exact form, say 3 square root of 3 divided by 2 instead of 0.87, unless we're going for a decimal approximation. But that's really just kind of standard stuff we'd expect from our homework sets. Any questions so far at the moment? Okay, as we can see, we're getting through lots of pretty interesting concepts in this course. We'll be hitting for sure on things like logic proofs, sets, functions, relations. Number theory is going to be one of our major things we're going to be looking into. And as time permits, we'll get into additional topics like the combinatorics, graphs, trees, and sequences. But I would say from here to here, this is the real meat of the entire course that we're really going to go for. And everything else is going to be additional topics towards the end of the class. Then it is, in a lot of ways, kind of a typical math class. We'll have 3 examinations, 75 minutes long, a 2-hour final exam, and these will be paper exams. So if you're in the in-person section, they'll be taken in the classroom. If you are in the fully online section, I'll be coordinating with you to determine which testing center works best for you, whether it's the Pocatello Testing Center, Idaho Falls Testing Center, and so on. So you'll always know what's on the exam, what's expected, since on the Canvas webpage, if you keep scrolling through here, as we get closer and closer to this date, I'll fill out the information of the exact coverage on the exam, review problems that you should be familiar with, and those kinds of materials. So the exams aren't meant to be kind of like the nastiest thing in the world. When it says a 75-minute exam, I'm trying to write essentially a 60-minute exam with additional 15 minutes for just double checking your work. So there's lots of stuff to say about the exams through all of this. Some of it doesn't even really make sense. For example, randomized seating chart makes really no sense at all for this class. I probably should have deleted this, especially if you're in the fully online section. They're going to take care of that in the testing center. The in-person section is pretty small, so I don't think we need to worry about that. But we'll come back to some of these things like the calculator for the exams and those kinds of things as we get closer and closer to our first exam. But I think we're doing good moving through the syllabus. Let's take a break. Any questions or comments so far? Okay. As far as the scoring goes in the class, oh, sorry, go ahead, Sophia.
Sorry, I didn't mean to interrupt you. I was just wondering, so for the online people, we just need to go to the testing center and take the exam there.
Yeah, that's correct.
Okay, thank you.
You bet. And no worries about interrupting. And there's always a little bit of lag when we're doing the online stuff through Zoom. So feel free to interject at any point. I'll never consider it rude. And yeah, if you're in this section right here, it's assumed that you're in the fully online section. I'll be sending everyone, pretty much everyone in the class, a direct email to verify, are you taking the exam in the classroom if you're in this section? If you're in this section, I'll determine which campus testing center is nearest to you. And as we get closer and closer to our exams, I'll send out instructions for scheduling that exam, where to go, what to do, that kind of stuff. Well, aside from that, looking at the grading here, this is our standard grading scale, but this course is heavily weighted on homework itself. Homework is the biggest component. Exams will be worth 15% a piece. And the final exam is going to be kind of low for a lot of math classes go for. 35% is usually on the high end. I'm going to weight the final exam as 25% in this course. Really, it's just an encouragement that the best way to learn material in this class, for any math class, but this in particular, is to really nail the homework. I'm going to be motivating how I write the exams based off what we assign in the homework. And when I go to assign the homework, I do these problems myself when I go to assign these assignments. After I do that assignment, that's essentially like my grading key. It tells me what should the lecture actually cover because it has to target the homework exercises. So I try to keep my lecture notes very close and parallel to what you're going to be doing on your own in assignments as well. So if you're doing great on those assignments, then the exams are going to feel kind of like a formality more than anything because, again, they'll feel almost like deja vu. The exams are based off what we did in the homework, which is also what we'll be doing in class in the lecture notes. And I think that's just about the major things I want to talk about on the syllabus. Scrolling through shows the day-by-day schedule when all the exams are. They're all going to be on a Tuesday, which kind of feels like it's always a little bit nicer since we can review material over the weekend. We have a lot of topics to get through, so you'll notice there's no reviews baked in, but I will accept any questions about exam one that you might have on the start of Thursday of this week right here. So if there's several questions that folks have, I'm very happy to spend a substantial amount of time discussing that exam. When we run out of questions, we'll just return to the day-by-day schedule. It is tentative. If we end up spending more time on some topic, maybe proof by induction is a good one. Sometimes to take an extra day on, we'll take that time. The only thing will be firm here are the actual exams. The final exam is going to be Tuesday, May 5th, warmer weather, 12:30 p.m. to 2:30 p.m. Well, that's the whole syllabus. Below are the university resources. Material probably you've seen before, but if this looks kind of like new stuff to you, that's good to take another really careful look at. But we'll close this out unless there's any last questions at the moment. Okay, let's close out the syllabus. And we're just about ready to start the course, but also I want to point you to just the various materials that are going to be updating day by day on Canvas. So everyone in the online section has found the Zoom link. And if you're also in the in-person section, if there's a day that's just not easy to come to class, I'm not going to police who uses the Zoom link. This is pretty much open to the entire course. Every course that we have will be recording, including this one. And that'll be helpful because if you're coming in, say in the online section in particular, if something happens to your machine or maybe your internet cuts out for some random reason, you could lose like 40 minutes of class just like that. But you can always just come back to the recorded lectures to see what we did if anything goes wrong. These are two optional articles for reading. There's a problem with this link here. I'm going to double check and try to fix. And we're going to be filling out these notes, the section 2.2 notes, and uploading all the solutions that we do in class. So if you ever want to come back and just see what the blank notes were, this is where they're all going to fall in, just on this folder here. So it'll just be a bunch of links to both the Word document, if you prefer that, or a PDF version. So that's pretty much how the Canvas is going to work. All of this is going to start updating on a week-by-week basis. Essentially, every time you log into class or come to class, I'm going to just be scroll to the current section that we're in. I'll say something like we're on example 3, and we'll just be updating these materials as we go. I post my sections piece by piece because I do a lot of heavy revisions on them. And for example, before I come to class and actually discuss the notes, I double check that my notes even make sense in the first place. I mean, that just sounds like decent practice. Just see if there's a mistake in the notes. And I found one today. Nothing too major, but I did make one change down here where it said evaluate. That's not quite the right wording because evaluation sounds more like you're putting something in a calculator, getting a numerical result. So I revised this one part right here to simplify. So I'll be working on the notes quite a bit. That's the reason why you don't see the entire course just pasted on Canvas. I wouldn't want to have to pull things off constantly as I'm revising. But occasionally something sneaks by, and if I ever have to put in a revision, they'll be indicated on the notes. Well, here's how the course is going to start. The lecture notes start off as a Word document, but it's the same file right here, except I didn't have the revision posted on this one because I felt like it was a pretty small one to change the wording to simplify. And I guess we're about ready to just launch the course. Starting with the definition of a Boolean value, we'll also look into sets of different numbers and look at interesting operations. When it says that arithmetic, we're going to look at interesting things like floor, ceiling, absolute value, modulus, and so on in these notes. That's a great set of notes to just contain a lot of interesting operations that are going to come back routinely throughout the course. Well, we'll start off on Boolean values. That's kind of a weird word. The first time I saw that, it just feels like a made-up word, but that's a real person, George Boole. So if you're interested in the background of this person right here, this is a nice little short set of reading from the Wikipedia page. He's credited with working on algebraic structures with something called Boolean values. So Boolean value is a value that is either true or false. It says next, kind of mysteriously, Booleans help us make decisions in code, whatever that might mean. And for a lot of the definitions, sometimes it's a good idea to just get a feel for what we're doing. There'll be a light example right below. So here's our quick example to go along with this definition for Boolean value. We know it's something that's either true or false. And now it says a light switch on a wall has exactly 2 states. Let's just assume that's true. There's no dimmer on that. For example, use Boolean to represent these states. And so a quick way to illustrate Boolean is we could say for state 1, maybe that's a default state of off. That might be someone else's non-default state, but let's make that our state 1. State 2 will be that the light switch is on, like in the classroom. And now we want to use Booleans to represent these states. Well, we have to decide what should off represent. Should this be a true or false? Any volunteers for a value for off? False. I agree with you. False just seems to make the most sense. Off feels like false on this. So let's call this one false. There's really no wrong answer to this particular kind of problem because it depends on what are you actually going to do with this Boolean state, making the decision of code. Depending on what you're doing, that might have made more sense as a true, but without any of that context, I think that's the most natural choice. Off should correspond to a false, on should correspond to a true. And then that's the whole example, but if it's going to help us make a decision in code, we might say program something additional. Maybe false is going to be a state where do nothing is our decision. Nothing is going to happen when the Boolean state is false. But when a Boolean state flips to true, we might do something, maybe in our kitchen, turn on a coffee machine remotely. You can imagine that's actually a pretty big project. You'll have to do some coding. You'll have to work with some hardware. Maybe Bluetooth is what you're going to go for, something else. Your coffee machine might have to be advanced, or maybe it's basic. Who knows what's going on here? But this is the idea with Boolean values. It's kind of a weird thing to introduce right here in the notes. It's the first topic in section 2.2. Author makes a big deal about it, and it's not really going to come back until chapter 3, but I felt like it was good to go along with the book on this one and introduce Booleans right away. Any questions about the definition at the moment? Okay, we'll be coming back to Boolean values once we investigate logic in different logical systems. But for the moment, the next thing we're going to look into is different sets of numbers. Actually, section 2.3 is already set theory, but sets are just so pervasive in mathematics, we can't get away with avoiding sets. We're discussing them right now when we go to the second topic, numbers. So here's a nice rundown of interesting sets of numbers that we need. First, we have the set of natural numbers. We'll be using that set of numbers when we do proofs by inductions quite often. And I've said the reason for the existence of this set, kind of just vaguely, there's a need for counting stuff. And this is blank for this object here. So this does it for a lot of people, but it turns out this set of numbers is just not sufficient for all things we want to do. This is the next built up set. There's different ways to indicate this set, but in our textbook, that Z with a plus is going to be the set of non-negative integers. So the only difference is we include a 0, and that doesn't sound too impactful, but it's kind of interesting to know that the number 0 as a mathematical concept was only really our earliest information on that came from, I believe this was India around the 3rd and 4th century BC. So that's kind of an interesting thought there. We kind of know what 0 means, nothing, but as a mathematical treatment, that took a while to actually come up with. And now it allows us to solve equations like these. X plus 5 equals 5 has no solution whatsoever in the natural number set because the solution is a 0 to that equation. So that's why we needed the non-negative integers. But then later on, we had to build up this set. We have to have that notion of negative integers as well, so that we can solve this equation, x plus 5 equals 0, get solutions like -5, and it just keeps going and going. What it feels like is a lot of the reasons for these number systems to exist is a need to solve more and more complicated equations. So 2x plus 5 is the next most built up equation. The solution is -5/2. But that's not an integer. So we go to the rational numbers, Q. Q is a strange symbol here. It's just mentioning quotient is the reason we use that symbol. Rational just means ratio of integers. And so now we can solve 2x plus 5 equals 0. Then it gets worse. If we try to solve x squared plus 5 equals 10, we have these two values as a solution, but these are not rational numbers. That's kind of a earth-shattering thing that happens in the development of mathematics. We had to have the notion of irrational numbers. This caused lots of drama in the era of Pythagoras. So together with the rational numbers, the irrational numbers, we form the set that you often hear about, the set of real numbers. As a number line, it's indicated as from -infinity to +infinity. Rather, that's in interval notation, not a number line. It's Q union I, And so that's our set theory symbol that came at us out of nowhere. U, not really written as U, more just as a symbol that looks like a cup opening upwards, is the union symbol. So its whole purpose right here by the red dot is just to say the real numbers are both the rationals together with all of the irrational numbers taken together. We fill out a continuum. There's now no holes in the number line from negative infinity to positive infinity. And we have a notion of every single number on the number line. The equations still can get even a little bit more complicated. Solving x squared plus 5 equals 0 has no solution in the real number system. So occasionally we have to use the complex number system, C, indicated in this way. It's A plus BI, where A and B are real numbers. And now we can get these kinds of solutions to form. So these are the different number systems that will be working throughout the book. Major reason for putting this all is just to help us get used to the notation as well. We'll see notation like N for the natural numbers, Z positive to say strictly non-negative numbers showing up a lot. We have to know what's meant when we see Q coming up and so on. Down below is just some light text that's describing everything that we just said in words, really mostly for the sake of completion. The table is the major object that we were wanting to investigate in this side of the notes. Well, so far, this is just lots of notation and kind of like a wall of text to get through. Any questions at the moment looking at these different number systems? Okay, let's try out some exercises relative to this kind of information. This one's kind of a light problem. What are the smallest and largest integers that are in the interval from 19 to 25, but not in the interval from 21 to 30? Really, this is just a kind of a light exercise to force us to think about what are sets in the first place, and what is this really referring to? This is just a subset of the real number system. So one way to express 1925 written in that very specific way, parenthesis around 19, bracket around 25, is this in set builder notation. It's a set of all elements x, such that x is a real number, said that in a funny way, all elements x in the real number system, such that is what the column here is going to be read as. 19 is less than x, is less than or equal to 25. So that's what that set refers to. And we're all pretty familiar with interval notation as we see it here. But really what we're practicing at the moment is getting familiar with set builder notation at the same time. The next set we're investigating is 2130. Bracket 21 means include 21. Parenthesis around 30 means we go up to 30 but exclude that particular value. So it's all x in the real number system, such that 21, to match that bracket, is less than or equal to x. And to match the parenthesis, we're excluding 30, so we say strictly less than 30 in this way. So now we know exactly what we're looking at. These two sets of numbers in particular. And now we have to solve this problem right here. I feel like these are pretty tricky exercises, really, because it says, what are the smallest and largest integers that are in the interval, first one, 19 to 25, but not in the second interval, 21 to 30. But one word in there is really, really important. It's this word. We're only looking for integer solutions to this problem. So that means we're looking into this set right here. We're looking for the maximum integer, the minimum integer. So when we say integers, we mean this set here. Anyone happen to see what it would be just through visual inspection, maybe imagining a number line in your mind?
It's 20 for both the largest and the smallest.
Yeah, absolutely. Thanks for spotting that. It's 20 for both, making it a pretty confusing question because that was pluralized, right? But you're absolutely right. The max for the largest is equal to the min is equal to 20. The max and the min are the same on this one. You know, it's kind of hard to visualize though. So this is what I would do personally if I want to be really, really sure I've got both the max and the min correct. Let's just draw these out. We want the smallest and largest integers in the interval from 19 to 25. Well, that means it starts out at a 19. I'll put a little open circle here to say we're not including the 19 specifically. It goes all the way up to 25. It also says, but not in 21 and 30. So here's one integer at 20. Here's the next integer at 21, but that one is also excluded. So the only candidate values would be somewhere between this set, but because we said integer, 20 is both the largest integer between 19 and 21 exclusive and the smallest all at the same time. So they're kind of fun problems in the sense that there's a lot to visualize, a lot to think about, and they're deceptively tricky sometimes when you do a couple of these exercises. Really, the whole purpose is just kind of warming up to sets, getting everyone on the same kind of page type of problem. Any questions or comments at all, folks, solving this one? Okay, let's move on to the next one then. Again, this set of notes has a lot of just random topics like these. But here's the next fun part. Some major operations that we're going to be using throughout the course is absolute value, floor, and ceiling. Actually, floor gets lots of use, which is really surprising. When we get into number theory, we're going to see that come back a lot, along with mod. Well, we're all familiar with absolute value. It's going to be the distance from your number x to 0 on the number line. It's a non-zero distance, non-negative distance. If you had to write it out as a piecewise function, here's what it looks like. Absolute value of x is just x if it's positive, or better to say non-negative when it's greater than or equal to 0, and negative x otherwise. But maybe the more interesting things here are floor and ceiling. This might be your first time seeing floor and ceiling, but you might possibly also seen these before. And that's what makes this getting everyone on the same page kind of section. The floor of a real number x written as that. It's kind of like a bracket where it's emphasizing the floor, the bottom, is the largest integer. Again, that's why we have to be really specific about what is our domain of numbers we're interested in. It's kind of like the last problem. This is all about integers. It's the largest integer that is less than or equal to x. There's a lot going on in this statement, and there's kind of a cross wiring going here because we want the largest that is less than or equal to x, and it's an integer. It feels like conflicting directions, even though it's not. So here's a fast example. We write 5.3. We want an integer that's less than or equal to x. Well, 3 is less than or equal to 5.3, but is the largest? Absolutely not. We can go a little bit higher. Anyone see what the true floor should be for 5.3? Absolutely. 5 is the biggest integer you can come up with that is still less than or equal to x, the thing inside. We can't go any higher because if we go 6, we've exceeded the 5.3. So that's the name of the game for both the floor, and if we flip it around, the ceiling function. It's written in the inverse way where the top is emphasized. So if we say ceiling, 5.3, then this time it's going to be the smallest integer that is greater than or equal to our x value, which is 5.3. Would you all agree that should be a 6? Awesome. So that's the idea between both floor and ceiling. Any questions at all, folks, with the definitions? Okay. Well, here's what the actual homework exercises are more likely to look like. Calculating the floor of this one seems kind of strange, except that's Euler's number. Anyone happen to know the approximation to that number E? I'm going to pull up a quick calculator. I usually try to remember to do this at start of class, but I was just a little bit more frantic than normal getting it going. So let's throw an E, and here it is. Euler's number is about 2.718. 281, 282, 46, and so on. Almost looks like it's a repeated decimal, but it's not. This one's irrational. And if you put in just about 2.7, that's a pretty blunt rounding, but that's okay because the floor of 2.7 is the same as the floor of 2.71 or the floor of 2.718 and so on. So I don't have to put in too much information here. Now we're taking the floor of 2.7. Anyone happen to have the value? Yeah, absolutely. From class, the value is 2. Next one feels like it's way more built up. It might also be harder to actually see. Let me see if I can bump that up. There's an exponent there. The exponent has the ceiling function, and then we're also taking the ceiling of 36/17. Feels like a lot's going on, so let's do this one a little bit more carefully. This is going to be the ceiling of, let's take 36/16. Excuse me, 17ths, so 2.1. And that's going to be raised to the power of the ceiling of -2.8. So the ceiling of -2.8, anyone see what that value should be? Smallest integer that, sorry, say again?
-1.
Ah,
2.
I feel like it's a -2 on this one, but suddenly it's a lot trickier, right? The moment you put a negative sign on there, it starts to get a little bit tougher to imagine. So sometimes it's not a bad idea to just go like this whenever this occurs. Here's one candidate, -3, another candidate, -2. That's a broken number line, there we go. Our number is here, -2.81. And let's revise. We're doing the ceiling, which is going to be the smallest integer that is greater than or equal to our value x. So that value -2 stated is that right value. Does that make sense to folks so far? Awesome. Sometimes this is not a bad strategy, it turns out. I feel like floor and ceiling are not too bad. But the more you put a negative in front of it, there's now suddenly lots of things going on. It starts to feel like a messier problem out of nowhere. So we're taking this to the power of -2. So that's not too bad. The ceiling of 2.1 is a 3 altogether. So this is just 3 to the power of -2. Now we're working a little bit with exponents. We'll do some of that work in our class notes today. This, in order to calculate, we can rewrite as 3 to the power of +2, flipping the sign of the exponent, and we just get 1/9 out of that. Well, part of the section is arithmetic, so there is a little bit of arithmetic to get through on this section. But any questions at all, folks, maneuvering through this problem here? Okay, it's kind of fun in a way. Again, the floor function is going to come back in lots of different kind of surprising ways. And one way it's going to come back is down here. Modulus is going to be one of our major operations. And modulus as a formula involves the floor of a particular fraction. So we'll be revisiting that once more when we come back to this part of the notes. There's a couple more things about exponents we'll take a look into. Let's finish off this last problem here. It looks kind of nasty. There's a lot of symbols going on here, irrational numbers of different kinds, floors, ceilings, and absolute value all in one. So if we were to break this problem down really carefully, it's going to be the absolute value of the floor of square root of 2 is about, I think this was 1.4. You know what? Let's just calculate that. Square root 2. Forget there's a calculator ready to go for us. 1.414 minus the ceiling of pi. Pi and square root 2 kind of go together in a nice way because pi is 3.141. It's kind of an interesting little coincidence with the first 3 digits in the expansion. Let me make that ceiling look a little bit more like a ceiling. Close the last delimiter, the one for absolute value. And this is what we're really doing. Irrationals are gone. So now we can run through the problem. The floor of 1.414 is just a 1 minus the ceiling of 3.14 is 4 itself. So now it's just absolute value of 1 minus 4. Absolute value of -3, producing just a 3 itself. So that's our quick tour of both ceiling, floor, and absolute value. Any questions at all, folks, running through these topics? Okay, next set of topics are really exponent laws, logarithms. I have a couple short exercises just like we went through. You're possibly very, very familiar with those kinds of topics. So think of this as really just brushing off the dust. If you're a little bit more rusty, it might be more impactful, but these are topics I'm not going to ask a lot on say exams, mostly to support other things we'll be doing in the textbook along the lines. Sometimes we have to be very careful with evaluating these kinds of things or simplifying them, as well as dealing with logarithms. So this is very heavy arithmetic review at the moment, but it's stuff that we should always be familiar with, ready to go with. So we'll do these ones carefully as well. First, here's just a really quick breakdown of what we mean by exponent notation. B to the power of n has a base b, an exponent n, and you could say informally, it just represents multiplying the base b repeatedly n times. That analogy does break down in different ways, but that's a great way to start thinking about what exponential notation means. It gets weirder when we're looking into these kinds of things. Multiplying by itself n times breaks down the moment you put in something like this as an exponent, an actual fraction. That could be 1/3, 1/5, 1/7, and so on. But all that really means is you're taking the nth root of b. So just as a quick review, if you say to the power 1/3, much like we see here, all this would really mean is you're taking the cube root of 2. That you can combine that with an entire fraction. If it's a power of m divided by n, you could express it as the nth root of b raised to a power n. But you know, this goes a couple different directions. B to power m over n, if it's convenient, could also be represented as the nth root of b to the power of m as well. Sometimes this is the most convenient form. Other times this one's the most convenient form. Just depends on the context. We've already used this definition once on the very prior problem just right over here, the exponent -2. B to the power of x is equivalent to 1 over b to the power of -x, and that's a often nice property to use. And then exponential things combine in these sort of ways for properties. Power 0 gives us 1, power 1 gives us the base, exponents add in this configuration, multiply here, and distribute here. So that's a really fast crash course on exponents, but again, I assume that we're all pretty familiar with this stuff. It's really just a refresher more than anything. So let's work out this problem. 16 to the power of 2/3. This means when it says simplify, by hand showing all steps, we're not going to throw this into a calculator. You might just double check the numeric value of your result to see if it's about right. We're just trying to put this in a form that's slightly more simpler than 16 power 2/3. There's a lot of ways to do this. We could say for attempt 1, if we follow the definition here directly, then 16 to the power 2/3 can be represented as 16 power 1/3 raised to power 2. And we could run it through this direction, but it's a little bit annoying if you really look at that. If that was an 8 to a power 1/3, it would just have been a cube root of 8 for an exact 2. We'd square it and get a 4, and our job is done. Or if it was a 4th root of 16, this would have been a nice problem. But this one is, while possible to keep going in this direction, I think it's trickier. Let's try it in a different direction using this formula up above here. The red dot is not staying put the way I'd like it to. There we go. So for attempt 2, another way to look at 16 power 2/3 is you could just say that this is the cube root of 16 squared. That might not look like the best way to go so far, but you know, you can do other interesting things with that base 16. this is the same thing as cube root of, well, 16. Oops, that was supposed to be a highlighter. 16 itself is nothing but 2 power 4 raised to the power of 2, which means this becomes the cube root of 2 to the power of 8. Really, the reason I like attempt 2 a little bit better is mainly because we're reviewing some of these properties as we go. We just used this property in reverse. 2 power of 8 can be broken down in that way. Now, if we're taking the cube root of this, 2 power of 8 can be broken down in using this property in a slightly more convenient way. It's the same as 2 power 6 times 2 squared. And now once we're here, we can break this up as cube root 2 power 6 times the cube root of 2 squared. And this is the part of the problem that simplifies directly. The index of 3 divides into the exponent, because really, when you say the cube root, you're just talking about an exponent of 1/3. That 1/3 multiplies through using this property right here. So when it's all said and done, you have this dividing into power 6, and now it's just a 2 to the power of 2. Multiplied by the cube root of 4. Now I'd say that's okay as a stopping point, but it's probably more traditional to rewrite that as 4, multiplying the cube root of 4. So kind of a strange problem. You could have gone forward in this direction right here, but for some reason I felt like this was the direction that made a little bit more sense to me personally. If you solve this problem slightly differently, got to an equivalent looking answer, maybe in a slightly different form here, then you did a great work on that problem. Well, any questions at all, folks, with the crash course on exponents? Okay, maybe slightly more interesting is if we reverse this, instead of talking about an exponential function, take its inverse and look into the logarithmic function, then we get these new properties. So logarithm to the base b of x is going to be written log base b of x. Again, this might feel like a review from, say, a pre-calculus course. It's a real number y for which b to the power of y equals x. So in other words, if log base b of x equals y, we can take this logarithmic form here and write it as b power y equals x. Because these are true bona fide inverse functions, really all that's going on here is the positions of x and the position of y just flips around in this expression. That's kind of hard to see if I leave that on there, but that's the main idea. X and y flip positions. And just like we had properties for the exponent functions, here's all the properties for the logarithmic functions as well. We won't be using a whole lot of these properties all over the place in this course, but I felt like it's rude to talk about logarithms without including all these interesting properties. And all of them are verified really just by this idea here. For example, log base b of 1 equals 0, the only reason this is true is because if you take b to the power of, take the answer, put it here, take the input to make it the output, so it goes here, that equation's true. And because this equation's true, it means the logarithmic equation is true as well. Why is this one true? Well, that's just a property of exponents as well. So properties of logarithms are really just repackaging properties of exponents, but looking into them in a different form.
I
And
got
all
a
of
question about that last property.
this one here,
Yeah, shouldn't it be the denominator on the right side should be log C of B, right?
let me see here. I got log base b of x. We're doing a change of base, so it should be log, the new base is c, but you know what? I think there is a typo. I think that one should have been an x right there. Thanks for spotting that. Yeah, this one was meant to be changing the base from a base b to a base c, but I should have had x in both the numerator and denominator position. Does that make more sense seeing it that way?
Yes, but if we do it like that, then it just simplifies to 1.
Oh yeah, you're right. What was I thinking on this one? Let me back this up a little bit. So log base b of x So this is what you were saying earlier, right?
Oh, so I think the denominator should be log base C of B.
Log base C of the old base B. Yeah, that makes a lot more sense. Yeah, well, it's getting a little bit rusty on that change of base formula. Thanks for your sharp eye on that one. Probably because that's kind of more of a major revision on that one. It's awful to put out a formula that's just incorrect. What I'm going to do with these notes is come back to here and just re-upload the revised version with the correct formula, both in here and over here as well. But again, thanks for spotting that error right there on the change of base formula. My attempt to try to fix it live didn't quite work out right with X and X in both spots. Does that look better to folks so far? Awesome. Thanks again for spotting that one. So that tells me that we're pretty sharp on logarithms for sure. And these ones shouldn't be too much of a trouble, except for part A is kind of weird because log 32, its value is really, really context sensitive. In a mathematics discipline, sometimes log is meant to be the natural log, not always, but in other contexts, like say statistics, log might mean log base 10 more often than not. But the context that we're working in the most is computer science. All of our big applications, essentially every single one of them, are going to be to computer science. Anyone happen to know what base that should be then? Yeah, absolutely. That was the statement over here as well, but you probably knew that by default. If we just say log in this course, because this is applied discrete structures with applications to computer science, we specifically mean log base 2 of 32. And anyone happen to have the value on this one?
5.
It'd be 5 exactly. That's correct. Why is it 5 exactly? It's because if you convert it to an exponential form, you have a true equation. So we can say this is because 2 to the power of the output, 5 right here, is it directly equal to the input of 32. So this table is really kind of profound in a way. It's a great way to just check your work. Understand the definition of the logarithm in the very first place comes right through this table right here. And that's the first logarithm done. Next one's not too bad. The base is 3. And you know what? 81 is a power of 3. 3 power 4 is 81. But because it's in the denominator, we have to be kind of particular with the value. Anyone see what the right value should be for this one? Yeah, absolutely. This one comes out as -4, and that's what's producing that fraction, 1 over 81. And if we do our quick check, all we're going to be doing is flipping around the input, the output, and reusing the same base. So here's my check. It's because 3 to the power of -4, by properties of exponents, is 1 over 3 to the power of +4. 3 power +4 is 81. And that matches the input of 1 over 81. So because this equation is true from the outer extremes we're looking at majorly, that means -4 is the right output to that logarithm. And the next last one is just kind of for fun. It's natural log -4. That might already throw up some red flags. If so, good on you. The base is base E. This comes from the French. This is really logarithm natural. They say things a little bit differently in the French language. So we're doing log base E of -4. And what would you say is the best response to this thing right here? Lots of things you could say.
I'd put log 2 of -4 over log 2 of E.
You could work that, but then you would still have a problem with both that numerator and denominator. That negative is actually causing kind of a weird problem out of nowhere. It turns out that this one is undefined. Or you might say not a number, does not exist. Anything along those lines would do just fine. It seems kind of weird out of nowhere we have an undefined. Let's double check this. Natural log -4 does produce undefined. But you know, the more and more mathematics you take, you might realize there is a way to define it. You just have to take a lot of coursework in complex analysis to see how to extend this function to the complex plane, and you can put a number down. It's just a complex number. This is undefined as a purely real number, is the way we'll say it. And a different concept is the function y equals log base b of x has domain, all valid inputs x, that's equal to 0. Notice the parentheses tells us you can't even put a 0 inside there. Take the natural log or any log whatsoever of 0, same issue, it's not a real number. The domain is a positive number off to infinity. So any non-negative number is valid. The moment we have a negative input or 0, we get it undefined on the logarithms. But we did it, folks. Any last questions about logarithms at the moment? Okay, well, that's kind of pretty fast tour through a lot of the different arithmetic properties that you're probably already familiar with the moment that you registered for this course, or maybe we're just brushing up just a little bit on these topics. Again, thanks for the help on the change of base formula right here. That was a surprise to me that that one was incorrect. I'll double check the rest just to make sure, but these look valid as I'm expecting them. The next part of the course is where things start to get possibly a little bit more new. You might have already dealt with modulus in a lot of different kinds of contexts, but the idea of modulus seems totally new to you. One thing that I should shout out is we're going to be using modulus in a lot of different surprising places. In particular, when we go to number theory in chapter 7, this is going to make a humongous comeback. So when it comes down to modulus, we're involved with non-negative integers, k, just like with the logarithm. N can be any integer whatsoever. And the entire structure, n mod k, that's kind of an interesting function because it's going to take two inputs, the n value you chose and the k value. It's equal to the remainder when we divide n by k. Or mathematically, it's this formula right here. N mod k is n minus k times the floor of n divided by k. That seems kind of weird and random, but you know there's a lot of ways to do these kinds of problems. If you're thinking in terms of remainder upon division, this does pretty good for us. Imagine dividing 17 by 5. Well, 5 times 3 is 15. We can't go in 4 times, so the remainder is 2 on this one, which means we automatically have a value on this. This one equals 2 for the modulus. So it's kind of surprising. These are pretty fast problems when we get started with them, but not all of them are as fast or straightforward as we would like. Notice part C is a little bit weird, negative 13 mod 5. You know, n is the value that we're referring to there, and all it had to be is an integer. We never said it had to be non-negative. K is the non-negative integer there. When you start to do these kinds of problems, this is where the formula starts to become really, really important. In fact, we'll be using a lot of these kinds of formulas down the line as well. So let's practice this problem right here, just using the formula, just as for the sake of seeing how it goes. So another take on this is that 17 mod 5 is the same as, well, the value n is the 17 here, so 17 goes into this position, minus the k value. The k value will always be the value to the right. It's going to multiply the floor of n divided by k, so that'll be 17 divided by 5. It's kind of interesting to see our floor function just suddenly getting involved with the modulus function. 17/5 as a decimal number comes around 3.4. Not around, it's exact. So we get 17 minus 5 times the floor of 3.4. The floor of 3.4 is just 3 right here. But then we've got it. That's just 17 minus 15, giving us the expected value of just 2 on this one. So there's a lot of different ways to do these kind of problems. If you can kind of just eyeball it and determine it's a 2, that's always going to be just fine. But when it comes down to these are ones where maybe a formula is going to be a good idea to use. Any questions on the first one, part A? Okay, part A and B really go together. It's a reminder that the order is highly specific with the modulus property. 17 mod 5 is 2, but anyone happen to see what 5 mod 17 ought to be? It wouldn't be 17, but you're kind of close. It's going to be one of those two numbers. Turns out it's just a 5 on this one. So 5 mod 17 is just 5. Why is that? There's two ways to check. From right here, it tells us that 5 mod 17 will be the remainder when we divide 5 by 17. But 17 doesn't go into 5 whatsoever, so the remainder is automatically just 5 itself. If we run into the formula, we would get the same exact thing. Just for the sake of practice, let's run it through the formula, see what it looks like. 5 mod 17 is going to be equal to the first value that came up, 5. My 17, that's the second value, k, that came up, multiplied by the floor of 5/17. So this becomes 5 minus 17 times the floor of, well, here's why it turns out to 5. This number is pretty small, right? Let's put it in the calculator. 5/17 is a 0.29. So the floor of 0.29, that's going to be exactly 0 on this one. So this is 5 minus 17 times 0, which is just 5 itself on this one. So either way you do it, if you don't use the formula at all in these exercises, I'm not going to be too worried about that. I'll just assume you're thinking along these terms right here, the remainder upon division. If you can do it by visual inspection and just say 2, that's okay with me on either a homework or an exam setting. But this one is tricky. Anyone happen to know negative 13 mod 5?
Would it be -3?
Turns out this one's not -3. This is really weird. And what makes it extra weird is that this definition is not 100% complete, fully accurate. There is a lot more to the modulus function that's really being said in this definition. A negative here is weird. And this turns into pretty much the #1 question that gets asked in this particular course all semester. Why was this value not what I expected it to be? It's compounded by the fact that different computing systems might give you a different value. The way our authors define modulus is in one very, very specific way. And the easiest way to see what this should be is run it through the formula. Let's make this our last problem of the day. Let's calculate -3 mod 5 and see if we can determine what does that actually mean geometrically on a number line. What did we calculate? So one more thing to think about when it comes to mod is that n mod k is a non-negative value. So we can't get a negative output to this one. The n value that we're throwing in is going to go in this location. The k value goes here. So if we run this through the formula, here's what we're going to get as a computation. First, it's going to be -13 minus our k value, which is 5 in this problem, multiplied by the floor of n divided by k, so that's -13 divided by 5 again. So let's do the floor of that one. Let's take -3 minus 5 times. Doesn't hurt to do this step by step. Let's throw it into the calculator as well. -13/5 comes out as a -2.6. Here, we need to be pretty careful as well. Anyone see what the floor of -2.6 should be? Is it a -2 or is it a -3 on this one? Let me see here. Yes, I think you're right. Absolutely, -3. I had to kind of imagine the number line in my mind to really see it. But exactly, -3 on this. We'll get -13 minus 5 times a -3. And it's all just order of operations from here, right? This is -13 plus 15, and it comes out as a 2. That's really weird, right? How do we take this information, take -13 mod 5, and get a 2 out? That's one of the biggest questions, again, that comes up this entire class, which is kind of interesting in a way. So let's end class by just giving a short explanation of what's really going on with modulus that's producing a value of 2 through this formula. And hide that one. We'll come back to that one when we come back to class on Thursday. So to visualize what's going on in this problem, when you say mod 5, the most important thing that you're really interested in is multiples of 5, positive, negative, or the 0 multiple. So we have -15 here. I'm taking negative multiples because the input n value was negative to begin with. So there's -15, -10, -5, and so on. When we took -13 and place it here on the number line, here's -14, -13, we're here. Not quite, let me fix that. Here's -13 right in that spot. And for our answer of 2, I'll put it in a box on this one just to emphasize it. There's 2 distances. This one has distance 2 to nearest multiple. And there's another distance to the nearest multiple from here to here. This has a distance 3 to nearest multiple. So if you allow negative values as an input to the modulus function, the interpretation that the author gave right above here has totally broken down. We need a new interpretation to see what's really going on. And this is what the mod function is doing in this context here. That value of 2 is the closest distance that -13 is away from, let me write this in a slightly better way. -13 is away from the nearest multiple of 5. So modulus is kind of an interesting function altogether. We'll be doing lots of work with modulus, like I mentioned in the later chapter, and it makes this formula pretty nice in a certain sense. You didn't have to use it even for this problem. You might have visualized it on a number line and just knew that -13 is 2 off from -15, and that's the shortest distance. And that's what's going on with these kind of moduluses. Some of them are fast to visualize, like 17 mod 5 has a remainder 2. Others totally break apart whenever there's a negative. Their interpretation changes on this one. Well, I think it's a good stopping point for us today. We'll finish off working through the last modulus problem, do a little bit of work with summation notation. Really just, this is a great topic to discuss pseudocode. But any questions or comments at the moment? Okay, well, we haven't finished this section, but if you're the person that likes to start the homework exercises early, you can get through quite a few of these problems. We are mostly done with section 2.2. But if you're the person who would like to just wait till it's finalized so you don't have to guess if we've done that problem or not, we'll finish these notes when we come back on Thursday. And so the due date will be a week away, the 22nd. Well, any last questions or comments at all, folks, before we call it a night then? Okay, well, the last thing I do after class is over is I take the file we're working on, convert it back to a PDF, and just override this file right here. So you'll always know where we're at any point in time. Once we finish off these notes, we'll just go off to the next section. I'll get the assignment posted soon as well for 2.3. But have a great afternoon, folks. If you do have questions, this is the part of the course where office hours essentially just starts right now. It's officially 2:30 to 3:30, but I'm not going anywhere. Occasionally, it might take a short break. So if you have questions, feel free to stick around and I'll be happy to engage with you. Otherwise, I'll see you all on Thursday's class.
Thank you.
Yep, absolutely. Thanks, you too.